Hi, I'm Chris Brown, and this is part 1.8 of an introduction to axiomatic design. So for the next 20 minutes or so, we're going to be talking about constraints. All right, first let's review the design domains. So we've defined 4 design domains that we're going to be using. Customer domain, where value is established. Functional domain, where we describe what something does. The physical domain, where we describe what it looks like, and the process domain, where we describe how we make it. So we refer to these by CNs for the customers, FRs for the functional, DPs for the design parameters, and PVs for the process domain. So restarting now. All right. Hi, I'm Chris Brown, a professor at Worcester Polytechnic Institute, and this is the section 1.8, or module 1.8, and an introduction to axiomatic design. So for the next few minutes, I'm going to be talking about constraints in design. First, let's review the design domains. We've defined 4 domains, starting with the customer needs, or the customer domain, and the elements of those are the customer needs. This is where value is established. Then there's the functional domain. The elements are called functional requirements, or FRs, and this says what functions need to be accomplished in order to satisfy the needs. This is what the design needs to do. The physical domain, with the design parameters, the DPs, this says what it looks like and how it's going to fulfill the functions described in the functional domain. And then the process domain, the PVs, the process variables, how to make the physical component. Now the constraints are a little bit different, and we're going to describe what's different about those. And these are things that the design should avoid. So we're going to see what those are and where they come from and how to deal with them. So here's how the domains are laid out. The customer domains lead into the functional into the physical, and the process, and the physical into the process, in a kind of hierarchy like that. Now I've not bothered to list out the details in the process domain, and there could be any number of FRs and DPs and PVs, as shown there as an example. There's 3 upper level FRs and 3 lower level FRs for FR1, but we could have any number. Alright, so the constraints come first from the customer needs. So there may be certain things that the customer is going to prescribe, and we'll be talking more about how to break those down later. Now those can impact the functional domain, the physical domain, and the process domain. Now, the other kind of constraint, or another way to think about constraints too, is they come from the choice of the upper level DPs. They put constraints on the lower level FRs. This is the way that works. If an upper level DP, say, is a hydraulic system, then the lower level FRs are going to be addressing the functions of a hydraulic system as opposed to, say, a pneumatic system or a mechanical linkage. Now, FR independence is part of axiom 1, and this is how it works with the constraints. So what if we have a candidate FR that cannot be separated from the other FRs? It cannot be made mutually exclusive. So it's inherently coupled. Now there's several things that, that are often inherently coupled to all the FRs. Cost, for example. It's hard to think of something, some function that isn't going to cost something to install. Time, time to produce, time in the way it works, so there's different manifestations of time. Overall size and weight. These often impact many FRs and cannot be made independent from the FRs. So then these would not be FRs, but these would rather be constraints. And so cost, time, size, and weight are typical constraints. Now, the special thing about constraints is that they do not take DPs. So FRs take DPs, but constraints do not. Now, there's different kinds of constraints we could consider, and all of the constraints should be known in a design problem. So, considering the different kinds of constraints can help be collectively exhaustive, so all the constraints can be known. Similar with FRs, we want to know all of the functions. So, input constraints, and these Nam Su defines in his 1990 book, the Principles of Design. So these are based on the design, and it shows how a component must fit with the rest of the design. And these are bounds on things like size, weight, and materials, and cost. And for these, lots of times we can use a budgeting process. So we can allocate different amounts of weight or cost to different branches in the design. And then you have a kind of negotiation between the different branches to see how, what proportion of the weight or the cost that they will have. Another kind of constraint that Nam Su identifies is system constraints. And these would be based on the environment in which they might function. So these could be interfaces, natural and man-made, laws, safety, that the design has to comply with. So these are natural and man-made laws. So obviously we have to comply with laws of design. Has to fit within laws of physics, for example, but also must be legal. So here's an example. So we have, say, a mount for a water pump on an internal combustion engine. So this interface is going to require a DP. The water pump has to have holes to align with the holes on the engine, and has to be able to seal with the engine, and it has to attach to the block. So the interface itself requires an FR-DP pair. So the FR might be provide sealed attachment to the engine block, and that could be decomposed further. And then the constraint, though, would be to stay out of the space reserved for the other components. And this is a constraint. And here's an image showing what some of the other components might look like on this part of an internal combustion engine. So classification of the C's. So this is helpful for identifying the different constraints. But the actual application in the design doesn't require that we're able to classify or say what kind of constraint it was. We have to recognize, however, that constraints are different from the FRs, DPs, or PVs. So, because they're not treated the same way in the design process. And the main thing is that constraints do not have corresponding DPs. If something needs a corresponding DP, then it's not a constraint, and it needs an FR-DP pair. So constraints generally influence several FRs, and they cannot be separated from these. They have limits rather than tolerances, and so the precise value of a constraint may not be important, but the limit, for example, the upper weight bound or the upper cost bound, would be important. The other thing about a constraint is that it's not adjusted in order to fulfill an FR like a DP would be. Now we have to be careful about over-constrained problems, because the constraints limit the design space in which we're able to operate. So it's possible to define constraints so that we're able to eliminate the space for any reasonable solution. So then we might need to see if we can change constraints into FRs somehow. So let's take a look at weight. This is an obvious issue in flying things. Now, it depends a little bit, right? So the FRs might be to provide for payloads. So we'd have to increase lift if we want to put more, a larger payload on a flying machine. So what would be the possible DPs? Well, within certain limits, we could say increase the power in a helicopter, increase the thrust in rocket engines, or increase the amount of lighter than air material in a blimp. Now and there's a limit, of course, to how far you can go with thrust and power and lighter than air material. So there are some constraints in terms of how much weight could be there. But we might be in a part of a design space where we actually could adjust the lift in order to comply with some needs for payload. Or it could be that the engine is already chosen for the helicopter, or the size is already fixed for the blimp, or the engine's already chosen for the rocket. So in this case, then we would have, then the weight would be a constraint. So every time we work on a design problem, there are some limits on the scope that we have to work within, and those will help us understand the constraints. The constraint might be part of a higher level in the design, and may be something that we can't address where we are in the design. Or they can just be physical constraints, in other words, limits on the amount of power that you can have in a vehicle. Now, constraints can be better than FRs. So, as we discussed earlier, the minimum number of FRs would be the best. So, the constraints will help us limit the number of FRs and could lead to a better design. But as long as there is still sufficient design space to find a good solution. And as long as we're not removing some of the design space where there could be important innovations, constraints could be better. So let's just take a look at how this works into the steps in developing a design solution. So first we look at the customer needs, and then we develop FR0 and DP0 at the highest level, and these are consistent with the customer needs. Then we develop the next level FRs consistent with the higher level DPs, which provide constraint on the lower level FRs, and the customer needs where other constraints could be contained. Then we select DPs corresponding to these FRs. And then we check the FRs and the DPs against axiom 1 and axiom 2 and the constraints. And then we modify and consider alternatives so that we can assure compliance with the constraints and the axioms. And then we go down to the next level and start back at number 3, developing the next level FRs. And we'll be talking more about how to develop those FRs in section 2. So anyway, we repeat this until we've decomposed the design far enough until the solution is obvious. So here's a little constraint exercise. And so with the appropriate phrasing, which we need to imagine, are these more likely to be constraints, FRs, DPs, or it depends? And if it depends, if so, why and how? So take a look through these and see under what situations they might be constraints, possibly FRs or DPs, and define the conditions under which they might be those. So this ends the module on constraints.